Hi everyone, we are back and we are going to solve our first problem set for the semester. So you all read that very fascinating article on gold nanoparticles, and we need to remember our materials tetrahedron. So I'm going to try to draw it very horribly, as we can see here. So what are the corners of our materials tetrahedron? So again, you read the article. It's a very good article. It's the author is actually a very good friend of mine, Reed Van Leen. That was some of his PhD work, and he had it was in collaboration with basically Daryl Irvine's lab, and it's a very interesting kind of finding that they had, which is that you have these gold nanoparticles that you're trying to, so gold nanoparticles, you have these lipids that you attach the gold nanoparticles, and you have a lipid bilayer which has hydrophilic heads, hydrophobic tails, and we want that gold nanoparticle to insert into here non-destructively and then, basically deliver drugs and all these other good things. So in that article, and actually the four corners of our tetrahedron, so we have structure, properties, performance, and then processing. Structure, performance, processing, and then properties. So, performance, properties, processing, structure. So how can we basically fill out our materials tetrahedron? Well, so what did they do? Basically, we changed the structure of this gold nanoparticle. So, we made basically the tips of these hydrophilic. They increased this size here to make them also, and actually to get them hydrophobic in here. Hydrophobic. So that we could penetrate inside here, and then they can stay essentially, actually you made most of this hydrophobic, but the gold nanoparticles would penetrate here. They would basically, the hydrophobic areas here would kind of wiggle and then stick in, and then the gold nanoparticle would basically, non-destructively enter there and stay within this hydrophobic region here. So it depended on some basically wiggling here, but eventually the hydrophobic regions, these hydrophobic tails here, would insert into here. And then the hydrophobic parts would stick out. So you'd have a gold nanoparticle that would look kind of, basically like this, and insert into that bilayer. So we changed the structure. The process was a chemical one to kind of chemically change here. So what happened to the properties? The properties of our our gold nanoparticle changed. So again, we kind of tailored essentially the chemistry on those hydrophobic, regions and hydrophilic regions, and it led to a drastic change in performance, whereas previously you could not insert them in. So it's just one quick example of how you could fill out that basically materials tetrahedron. All right. True or false, and correct if false. Ionic bonds can reform at room temperature. No, those are intramolecular bonds. They have energies way larger than 1 kT, so they cannot reform. So that is false. The only ones that can reform at room temperature are the intramolecular interactions, van der Waals, H bonds, things that are less than 1 kT. Intramolecular have energy greater than 1 kT? Yes, that is true. All of them which are ionic, metallic, and covalent. Constructive interference leads to no signal on the intensity versus 2 theta curve. No, that is not true. Destructive interference would lead to no signal. To measure atomic distance, I can use microwave. No, atomic distances are what distance? Angstrom. So I need copper alpha radiation. I need 1.54 angstrom wavelengths approximately. Microwaves are micro. That is way larger. We're not going to be able to do that. Bragg derived his equation by realizing that constructive interference between waves has a mathematical relation that leads to perfect amplification. Yes, that's pretty much true. Perfect amplification is really where you kind of see the kind of key distinction, but yeah. So that's a little bit of a little funny phrase there, but yeah, that's pretty much true. Extra distance that waves must travel via the Bragg angle must be more than 2 integer wavelengths in order to achieve destructive interference. No. It needs to be an integer number of wavelengths. So, and then that is constructive interference. So, there we go. All right. Classify whether the statement's true or false. Again, okay. Metallic bonds are intermolecular. Nope. They are intramolecular interactions with an energy of around 100 kT. That's a little bit less, but again, give or take. But those are intramolecular. Intra. Intramolecular interactions can break and reform. Yes, that is true. We just said that. Ionic bonds gains or lose electrons. Yes. Van der Waals bonding has delocalized valence electrons. No, that's metallic bonding. Magnesium is a cation with a 6+ charge. No, magnesium is 2+. Van der Waals interactions are intramolecular interactions greater than kT. No, they are inter, and they are less than kT. All right. What type of bonding will be exhibited by chromium? Chromium is a metal. It will do metallic bonding. It will not break and reform at room temperatures. The electrons are delocalized, as we talked about, so they can fly around, and hence the electrical properties of metals. CaCl2. Uh-oh, how are we going to do this? Actually CaCl2 and MgO. So I need Ca, I need Cl, I need Mg. O, I think is 3.16. But let's look at electronegativity. So to do that, I'm going to have to find, where is my, do I not have my handy periodic table up here? All right. Well, you know what that means. We're going to have to go into Canvas, and you're going to have to basically sit here with me while I look at this. I think it should be an uploaded media. I should always have this. That is not the right course. Let's see, uploaded media. Come on, let's get our... Is it not an announcement somewhere? Let's look at it. Let's see what we've got. Here we go. Here we go. Let's download this. This is the penalty you have to pay for me not having this periodic. All right, so let's look at the periodic table. Let's insert file printout. Here we go. And we will go ahead and get this uploaded here. Just take your time, relax before we get into our whirlwind of basically our Pset 1 solutions. And here we go. All right, so O, we are going to be looking at electronegativity because that's how we're going to tell our difference. So let's see, where is our electronegativity? I think I don't. Polarizability, En. Where is it? Maybe on a different slide here. Here we go. Electronegativity is going to be the bottom one here. Fantastic. So we did have Ca, so it's basically the second one here. So Ca is 1. So let's go ahead and write that down here. Ca is going to be 1. That's very lucky. CaCl2, I shouldn't have gone over here so quickly. I need Mg, and then O and Cl. I need Mg should be right here, 1.31. 1.31, and then let's go to the other side of the table. And O is 3.44. I'm losing it a little bit. And then Cl is 3.16. So I was close. So Cl is 3.16. Oops. 1.31, 3.16, 3.44. And so remember, our rule is, I believe, in our lecture notes, that what was our rule for ionic versus covalent bonding? Although usually there's never really a true covalent versus ionic bonding. But we said, remember, in our notes, we had a certain rule that we were going to say. So we said greater than 1.7, then that's going to be ionic. So we can see that for all of these, actually, let's go ahead and make this calculation real quick because we're going to need to use this in just a second. So let's pull this up. So let's just make sure our math is correct. So our materials were CaCl. So Cl is 3.16 minus 1, 2.16, hopefully. Let's check if Mathematica is right. So this should be ionic bonding, because greater than 1.7 is going to be ionic, less than is going to be polar covalent. And it's thinking, and then we could do the 3.44 minus Mg, which 1.31 1. And it's thinking, and while this thinks, that one's going to be a close one, but I think these should be both ionic. Let this guy think, 2.16. Yep, we are ionic. So there we go. They're going to share electrons, and peak is going to be a polymer. Polymers are going to have covalent bonds. You can see in peak that it will also have basically intermolecular interactions. And we can actually look at PK molecular structure. So we can look at peak, and we're going to see not only, basically, you're going to see these polar bonds here. You're going to see these big steric interactions between these, basically, these aromatic carbon rings. And so you're going to have lots of intermolecular interactions as well. So that's it. So let's go ahead and let's move on to number 5 now. All right, so we know that Cl in number 5 is -1. So we know that B is going to be 3+ because we have 3 of those Cls. So B is our cation. That's the valency. And then Cl is our anion. So B is going to give up electrons. Cl is going to gain the electrons. V2O5, so again, we know O is always going to be 2-, so that's 10 of those. So V is going to be 5+. So cation gives away, anion grabs. Cr2O3, again, O is always 2-, so we know that Cr is going to be a 3+. And again, cation gives away electrons, anion grabs electrons. Fantastic. All right, so we discussed different potentials in class 1, most ubiquitous being the LJ potential. Had a colleague run a simulation for chromium. So let's go ahead and let's get this. So I have my LJ potential, VLJ, equals 4 times epsilon ep times sig divided by r to the 12th minus sig divided by r to the 6th. So we know that here we've actually been assigned epsilon is equal to 0.6 joules. Sigma is equal to 4.4 angstroms, so times 10 to the -10 meters. So let's put those here. And what is the equilibrium distance between chromium atoms? So we need to go back. So periodic table. I need to look at basically distances. So metallic radius is going to be the second one down here. I need chromium. Chromium is telling me to do, where is my chromium, or where is my chromium? Chromium. Here it is. So 1.3 angstroms is my R, but I know that distance is always 2R, so 2 times 1.3 times 10 to the -10 equals CrEq. Chromium equilibrium distance is this. What is predicted by equilibrium distance here? I need to basically take the derivative of my VLJ with respect to R. I need to solve when does this equal to 0. So this equals 0 in terms of R. Whoops. And solve. And okay, so this is quite different from what we're expecting, but hey, that's the problem set. So it is different here. What distance is the force maximized? So I know that the force equals minus the derivative of VLJ with respect to R. So where's the force maximized? Well, I could solve force, or actually take the derivative of force with respect to R, set this equal to 0, solve for R. So the distance where the force is maximized is this distance here. And we're asked what is the force at a distance of, so 4 / dot, R goes to 2 times 10 to the -10. That would be my force right here at that distance of 2 angstroms. And draw these locations on Lehringer's potential, explain the results. Stiffness of the material can be predicted by the curvature of the potential. Mathematically, how can you determine the curvature of a function? Curvature is the second derivative of our function. So that's just a kind of a quick one. But here we go. Let's see our Lehringer-Jones potential. So we know basically ULJ looks like this. Oops. Let me go draw this. So here, curve looks like this. So we predicted that our equilibrium distance is about 4.9. So let's say, so it's about 5 angstroms here. We're maximizing our force F max right here. On this side, we're repelling. On this side, we're attracting. So basically two angstroms that are really repelling, pushing away from each other. So way over here. So that's bad energy. Low energy always wins. And that's it. That is your first problem set. So thank you, and I will see you all next time. Have a good one. Bye.